So, hello everybody, this is Luboš Pirkl from CFD Support. I am here in our Prague office with my colleague Radek Máca. Hello Radek.
Hello, Luboš.
How are you today?
Yeah, I'm fine and ready for the webinar. Thank you for asking. And how are you?
So fine, thank you. Okay, and together with us on the other line, there is Oliver Felde from CFturbo in Dresden. Hello, Oliver.
Hello, Luboš, how are you?
I'm fine, thank you. Yeah, so are you ready for the webinar?
I am, yeah, and I'm happy to be with you together again on that webinar.
Okay, thank you. It's great to hear this. So I think we can start. So hello again, everybody. Welcome to the webinar on turbo machinery design and analysis. In today's webinar, we would like to show you an easy way how to design a centrifugal compressor from scratch in CFturbo, and then how to simulate and evaluate it in turbo machinery CFD. The webinar is being recorded, and its recording will be made available on our YouTube channel. I hope everything works well, all the techniques is all right. In case of any technical problems, feel free to contact us. We will gladly answer all your questions and comments afterwards. So please let me start with who we are. I'm going to introduce us a little bit. So this is me. My name is Luboš Pirkl. I'm co-founder of CFD Support. I am here in our Prague office with my colleague Radek Máca. Radek is our head engineer and senior developer here at CFD Support. And finally, in Dresden, there is Oliver Felde. Oliver is senior manager CAE at CFturbo. He is responsible for consultancy and software development, especially for the implementation of turbo machinery design theory and related algorithms in CFturbo software. About the program, the webinar is going to take about 1 hour, depending on the number of your questions and comments. There will be basically 4 parts in this webinar. In the first part, there is this general introduction. In the second part, let's call it the design part or CFturbo part, there will be a live example where Oliver is going to introduce CFturbo a little bit, and he will show a live example of centrifugal compressor design in CFturbo software with final export to of the designed model to the turbo machinery CFD. In the next part, we can call it simulation part or turbo machinery CFD part. There will be the other live example where Radek is going to show you turbo machinery CFD simulation and evaluation of that centrifugal compressor exported by Oliver from CFturbo in the previous part. And in the last part, finally, there will be a Q&A session dedicated to your questions and our answers. Feel free to put your questions to the special window, or you can also send us an email to info@cfdsupport.com, and we will gladly answer all your questions later in this webinar. Feel free to put your questions. This is quite important part. It's your time. We are here for you. We are ready to answer, to tell everything. So take your chance. Okay, so I think we can start with the CFturbo part. So I'm gonna hand over the presentation to Oliver. So Oliver, will you tell us about CFturbo?
Yes, I will. Thank you, Luboš. Okay, CFturbo is a company based in Germany with 2 offices in Germany, in Dresden as well as in Munich. Our main product is CFturbo, a design tool for the turbo machinery design of all components related to turbo machinery. We call it conceptual design software because it's not based on geometric input data but on operation input data, and it's therefore based on latest design theory. Right now we have 200 or more than 200 active clients globally, and CFturbo, the software, is split into different modules. One can use those modules to design pumps, both axial and centrifugal, fans and blowers, again, axial and radial, compressors and turbines, and of course complementary components like stators and diffusers, as well as volutes. And with our software, we serve the following industries. Amongst them, there are aerospace industry, automotive, home appliance applications, energy, oil, gas, marine, mechanical, process engineering, semiconductor industry, and so on. So that's quite briefly about CFturbo.
Okay, so yeah, I think it's your screen now is gonna be so.
Okay. You should be able to see my screen now.
Yes, we see it. It's perfect.
Okay,
So
thank
go
you.
ahead.
Okay, so that's the GUI if you start CFturbo, and what you see is the 4 different machines you can design with CFturbo. Today it's a compressor webinar, that's why I'm press this soft button. And the first thing, if one starts to design something from scratch, is the definition of the global setup, where the best point is to be defined, because right now we do some sort of best efficiency design. And the example I want to show is a rather small compressor that has a mass flow of 0.18 kilogram per second, a total pressure ratio of 3, and it runs on 65,000 RPMs. Also, it should compress air, and when it comes to the definition of the fluid, one can choose between different real gas models given here, and also, of course, with perfect or ideal gas properties. And if I click on that right button here, it gives you also the chance to have access to other gases, and also you have the opportunity to add new fluids that just have to be defined by some general properties like gas constant or critical values and so on. Okay, also one should define inlet conditions, because they are of course important for the thermodynamic calculations. Once that is ready, one is asked to add a component. I want to start with the impeller, because that's the central component of that compressor stage, and that's why I'm clicking on the radial mixed flow impeller. And again, what follows is this dialog is opened where one has the chance to define the main dimensions. The main dimensions are just the inlet diameters, the impeller's diameter, and the outlet width. So what I want to have is an unshrouded impeller with a certain tip clearance, for instance 0.4 millimeters, and it should have splitter blades, of course. On the second tab, there are a couple of parameters defined which can be adjusted by myself, and they are taken from a wide variety of publicly available data. So for instance, the diameter coefficient is just taken from the well-known Cordier diagram for a certain specific speed that comes again from the global setup, and a default value of 2.8 something is given here, but of course can be adjusted. Also, what is very important is one has to have an idea about the efficiency which can be reached with this kind of machine. And again, there is something implemented in the software, and also the source is given. This is from Klaus Lütge's textbook, for instance. And it's important that those values are realistic and reasonable. Otherwise, you would not get good proposals by the software when you, for instance, press this calculate button, or if you just have this checkbox checked where every change of a parameter is followed by a recalculation of the main dimensions. And those recalculations are done on the basis of just balance equations and the empirical formulas that have been implemented. Okay, I want to just make or want to get rid of that decimal places, and that's why I'm just make it those values to round values. So for instance, 60 millimeters in diameter and maybe 4 at the outlet width. On the right hand side, you always get some information about average values that can be calculated just with the use of the gas description and the balance equations and so on. And you will always get some sort of a feedback what is in which scope your machine will run. Also the average velocity triangles are given at this point. Okay, next step is to define the general meridional contour. Here one can define the actual extension of the meridional contour, but not the diameters anymore, because they are set in the design step before, and if one wants to change that, one has to go back to that design step and has to change it there. At any time, one can do a right click and type in some coordinates, and the contour itself is described by just Bézier splines. Again, there are some informational things that can be used to check the design. So for instance, a potential flow solution for the average meridional velocities or potential flow is given here together with the vectors of the flow. Also, curves about the static moments and the area progression and so on are given here, and they are recalculated after any change of the meridional contour. Okay, once I'm happy, I can go to the next design step, and the next design step is the definition of the blade angles at leading and trailing edge. It's important to set the general blade shape here because there might be some restrictions which can come from the manufacturing or from the general operation, the operational regime in which the compressor has to be run. So very often the compressor wheels are flank milled, and that's why one should go for ruled surface 3D blade shape. When this is chosen, one can only define blade angles at hub and shroud, because in between the blade is calculated in accordance to that blade shape. Also, blade thickness has to be defined here at leading and trailing edge, because that is used for the calculation of the velocity triangles. And last but not least, a slip model has to be specified, because there is always a deviation angle between the direction given by the blade and the relative flow, and that deviation angle is calculated in accordance to the chosen slip model. And what I have done here is the Angier-Wiesner model, and if I press calculate, then this yields some some angles at leading at trailing edge. Once I'm happy, nothing more has been established here, but it gives me the chance to go to the 3D model that has been developed so far. The only thing we see right now is hop and shroud 3D geometry plus the location of the leading and trailing edges of main and splitter blades. Okay, in order to finish that design, I switch to the next design step, which is called meanline design. And here again, we have those two, what I would call master mean lines, which are hop and shroud, and only those can be manipulated. So what we can do, for instance, is we can grab this Bezier curve in MT coordinates and change, for instance, the rep angle, and we can change the inner Bezier points and get here with some other blade angle distribution between leading and trailing edge. Again, on the right hand side, there are some information which can be used to check the design. So for instance, there is a rapid relative velocity estimation on the basis of Stanitz and Prine's approach from the 50s. There's again a blade-to-blade potential flow estimation given here, and also some geometric data can be taken from the right hand side, for instance, the lead angle, which is given here. At every time step, there is a 3D preview, which I would like to open here. And here, for instance, we see the current design. And if I want, for instance, to change the lean angle at the inlet, I can change the leading edge position of span shroud, for instance, and then it will look immediately like that, and it also will give a different rake angle. And to make that a bit less harsh, I try to increase the wrap angle of the main blade at hop and shroud. Okay, and then it would look like that. But as you see probably here on the right hand side, there are not everywhere with that simple velocity estimations, there are not everywhere solutions possible because the choking throat might be too small. But again, one has to have in mind that this is based on potential flow theory. Okay, once I'm happy with that, I can press OK, and in 3D now I will see the blades having a zero thickness, and that's why I put now some thickness on it in a very simple way, just by adding perpendicular to the mean line some the thickness already defined in the blade properties. Again, the preview will show now the 3D geometry of the blades, but now it still has sharp edges, and in order to get good design edges, I open the last design step, and this is where I can give, for instance, the leading edge an elliptic shape, and where I can tell that the trailing edge should be trimmed with the impeller diameter. And again, the 3D preview will give some impression on how it will look like now. You see the rake angle is quite big here. Okay, and if I go back to the 3D model, I'm done. So it's my initial design, but it's just the impeller. I want to do a complete stage. That's why I'm going to add an pinch type stator, and the stator should be just radial and should have a constant area here. Let's take a length of 3, and let's go to the very next design step. Make it less hard changing, and so that's probably the pinch type diffuser, and then I want to have another diffuser that should have parallel walls, and again it's radial, and it should have a certain length, so for instance 10 millimeter at harp and shroud, and I don't need this Bezier shape because it should be just parallel. And if I go through the 3D model, I now have a 3D model including diffuser, and the last step would be to add a volute. Here again it's structured in a similar way as the impeller design. So there is first an kind of main dimension definition design step, where just the inlet diameter and the inlet width has to be defined. I'm going to have a 6 millimeter width, and when I press OK, I have the chance to define the general shape of the cross section. I'm going to for asymmetric round blade shape, but I could have different sections, and I could also have it non-symmetric, and so on, if I use those half symmetric shapes. But that's nothing I want to show right now. The next design step is the actual scaling of the cross sections with the rep angle, and here I'm using Flydor's rule with a swirl exponent of 1. I can use again the 3D preview, and we'll see what happens here. If I press OK, I'm already done, almost done. The last step would be the definition of the outlet diffuser. That should have a certain height and maybe also a certain outlet diameter. Again, preview gives me that component, and if I'm happy with that, I see how my 3D model has been developed over the design process, and the only thing that is missing now is just the definition of the cutwater here, because you see that there is a certain intersection between the spiral and the outlet diffuser. And that's done in the last design step. Here one has different design modes. Again, the most elegant one is probably the fillet radius, where you can define a certain radius. And if I do the update, then you see how this is done. And if I go back to the 3D model and waiting a bit, you see here how the fillet cutwater has been developed, and I'm almost done. I want to change this thing. It's a centrifugal compressor with a certain pressure ratio. That's why I'm call it like that. And because that was based on 1D design theory together with some empirical knowledge, of course it has to be validated. And to this end, one should probably introduce another stator right at the inlet of the stage. And this can be purely axial with a certain length. So for instance, I don't know, 80 millimeters. And just very quickly finish it by just make that straight. And in 3D it looks like that. Right now I don't have a spinner, but I could add a spinner here, and that then would be a pure pipe in front of that. But I want to save time, and that's why I'm just want to show you quickly how to start the validation process. And to this end, one can change from different CFD export interfaces, and the one we look today is the Turbo Machinery Design CFD interface. One has to get rid of the space in the name, and I also have to have a gap here. But just to show you how to proceed with that, I'm open the parameters panel where you can set some STL parameters. And if I sort out these messages here, or the things connected with the messages, I can start the export. And then the STL files will be written together with a control file, which can be used by TCFD. And saying that, I'm finished with my little presentation, and I will now give the presenter to Radek.
Okay. Thank you, Oliver, for the turbo machinery design part in CFturbo. So now we switch back to the original presentation, and yeah. So now it's time for the simulation part. So it's the turbo machinery CFD part, and before we go there, I would like to remind all the attendees to put their questions. We mean it. We would love to answer them later in the webinar. So feel free to put your questions right now, and also anytime during the webinar. So I will give a brief description what is turbo machinery CFD. So let me just quickly go through that. So Turbo Machinery CFD is a unique software developed by Czech company CFD Support. It is smart, easy to use, and affordable CFD software. Turbo Machinery CFD was designed for CFD simulations of all rotating machinery, such as fans, pumps, compressors, turbines, turbochargers, hydro turbines, etc. Almost all of them, or at least all the standard machines. Both radial and axial machines, both compressible and incompressible fluid flows. Turbo Machinery CFD is based on OpenFOAM, and we believe Turbo Machinery CFD is unique, at least for 4 reasons. Number one would be Turbo Machinery CFD has no licensing policy, which means our clients can keep Turbo Machinery CFD forever, and they can use it for unlimited number of users, jobs, or cars. What is paid for is the fast delivery and technical support and software maintenance. This gives the investment in Turbo Machinery CFD permanent value, of course. And also this means our clients can scale their CFD simulations in a really big way. Number two would be Turbo Machinery CFD is fully automated, which means all the workflow from the initial data to the final engineering results, it can be run by a single click or by a single command. And all the process is being done automatically, and for these reasons, Turbo Machinery CFD is extremely effective. Number three would be we believe, or we deliver the extraordinary technical support. We are proud of it. We feel custom approach to every customer, to every issue. We never leave behind any of our clients, and we are very flexible in it. The technical support is unlimited. and we support our clients even in matters out of the turbomachinery field, for example, in numerical mathematics, physics, general CFD, IT, or even software engineering. And number 4 would be the real tutorials are included, so turbomachinery CFD user has no doubts about the best practice settings. So there are included the real machines that are already preset. So basically the user can take one of these tutorials, replace the geometry with his own. He can modify the settings and just run the simulation. The rest of the workflow is automated or can be automated. And also the minimal requirements on the user's CFD skills are very low because of this. And yeah, this would be it. These were the basic benefits. I think there are even more benefits, but I'm not going to go for all of them. I finish here with my last point that at CFD support, we believe the future of CFD is the automation. We believe that in CFD everything can be automated. The automation is extremely effective. It's even more effective than we expected in the first place. So just I finish with my last point that nowadays at CFD support we only think in automated sense. It brings a huge value to everybody, especially to our customers. So it was just a brief description of turbomachinery CFD. Now it's time for the live example. So Radek, are you ready with your contribution?
Yes, I am. So please, can you hand me the
Of
presentation?
course. So now here you go.
Okay, so I hope you see my screen.
Yes, we can.
Okay, perfect. So thank you, Luboš, for introduction, and good afternoon, everybody, or good morning. This is Radek speaking. Yeah. So first, let me briefly introduce the outline of my part of today's webinar. So I'm going to show you how easy it is to work with the turbomachinery CFD in general. We are going to use the export from CFturbo, which makes the workflow even simpler. So as you will see with CFturbo and turbomachinery CFD, we are now able to run a CFD simulation and get significant results just by a few mouse clicks. So I will show you all steps of CFD workflow, which is case and computation setup, running the simulation, and results evaluation and post-processing. So let's start. We simply start from data which Oliver has generated and exported for us. So this is how it looks like. Basically, there are two main parts. First is the configuration file, in which, okay, so I will use my favorite file browser. Okay, so the first is the TCFD file with predefined or defined the computation or parameters for the computation, for definition of the geometry, and so on. So this was automatically generated from CFturbo, and I modify it to simulate more speed lines and more points. So this is the first file, and the second one is the directory with STL files, which defines the geometry. So this is also automatically generated from CFturbo. So you can check it by click on the particular file. You can check, for example, the blades and see how the input geometry looks like. So this is standard STL format with triangulated surface. So this is the input. And yeah, you can also start from scratch. So to start constructing your own case with your own geometry, but we with connection with CFturbo, the job is more simpler. And there is basically, for the first computation, there is no need to modify anything. So to start working with the TCFD, we need just to click on the configuration file, and new ParaView session will appear automatically. So we have developed this graphical user interface directly inside the ParaView, which is a standard third-party software directly delivered with OpenFOAM. And here we can set the CFD computation, run the simulation, and post-process the results. So it means 100% of workflow can be managed directly in this graphical user interface. So as you can see here in the pipeline browser, the configuration file is directly loaded. So to start using it, we need to click on Apply button. And because all is preset, so after the click, we can see the input geometry, which is built. Okay, sorry, it was too fast clicking. So you can see directly the input geometry, and in the right panel there is a list of all parameters which is set, and its values which are set for the simulation. Okay, so you can change and define anything which is connected to the simulation directly here in this left properties panel. So I will go just quickly through this, and I will show you what can be changed and where. So there are several menus. For example, in general, you can load different configuration file, you can save it, and so on. You should choose which machine you would like to simulate, because each machine includes different setup. Then there are several menus which defines the basics, which is coordinate system of rotation, which defines some geometry scaling if the input geometry is in millimeters or meters. Physics, so here you define the physics of the fluid. The standard setup is air or water, but you can define any parameters which is related to your fluid. Turbulence modeling, of course, you can distinguish, or you can set the K omega SST laminar or K epsilon at the moment. The important part is the speedlines part. So here you define the points of simulations. So first you can define a number of speedlines, that is the simulation with different rotational speeds. And for each speedline, you can define several points to be simulated. So usually each point carries different boundary condition, for example, different pressures at the inlet or at the outlet, different volumetric flow rates, and etc. For each point, you should define the maximum number of iterations to be computed for each speedline and each point. So here I have defined 6 points for each speedline. And as I already said, each point carries the different boundary condition. So for example, here we are using at the inlet total pressure and total temperature boundary conditions, and at the outlet we are using special outlet vent boundary condition, which somehow simulated the different pressures, but using this outlet vent, it can follow the better whole speed line, and it is really useful to generate whole compressor map. So here we define the boundary condition. Inside the simulation there are several parameters, but I would like to mention just one or two. This is processor number. For example, my laptop has just 4 cores, so I have to change it to 4, because a higher number makes no sense to define, and it will just slow. It will make the simulation slower. We also provide both steady state and transient simulation. So here I will simulate just a steady state. Inside the numeric, there are some parameters related to the numerical schemes. Of course, initial conditions, so define a reasonable initial guess for the computation, and important menu, which is the components one. So this is important if you're starting from scratch without CFturbo export. So you have to define each component, you have to define each boundary, physical boundaries, and so on. So here we have 4 components, so it basically follows the export from CFturbo and the construction workflow for each machine. So basically here you define several components, and if you're starting from scratch, so for each STL you should define the type of the boundary. If you are not using the external mesh, and so this software uses SnappyHex mesh to generate the computational mesh, so you define some minimum and maximum refinement level, boundary layers you can define, and the communication between interfaces. So it means interfaces between 2 different components. In general, we also provide, or this software also provides the usage of an external mesh. So you can distinguish here. So external OpenFOAM mesh, it means you can use almost any external mesh which is converted to OpenFOAM and use it for the simulation. So other parameters are related to the SnappyHex mesh, which defines the maximum size of the cell inside the geometry and so on. Here, this is a nice sketch of the mesh topology, let's say. So it's really useful when you starting from scratch and building the mesh from the very beginning. So you can see the topology, which part is connecting to which part is rotating, and so on. So other 4 menus are related to the SnappyHex mesh, and it basically contain any parameter which SnappyHex mesh uses. The last one, or not the last one, but the last 2 menus, there are post-processing, so you can check different boundaries to evaluate efficiencies, pressure drops, and so on. And also it includes the scripting part, so you can load a simple Python script using which you can add your own post-processing feature, or you can define, for example, different turbulence model which is not implicitly defined here in the turbulence menu, and so on and so on. So whenever you are satisfied with your setup, so you should confirm it by clicking on apply button. So now the current setup is saved. So this was the setting or set, or this was the first phase of the CFD workflow. So setting of the geometry and the physical parameters and so on. So now we would like to manage the simulation. So to manage the simulation, we need to just click on the settings item here, and then there is an icon which is called TCFD manager. So I will click on it, click on apply to enable it, and now we can see here several or new bunch of buttons, and here I will explain how to run the simulation. So first we can set up the directory name in which the results will be stored. So for example, my case, anytime I change something, I need to click on apply button to confirm it. Now I need to click on write case, which automatically creates the case structure directories and all compulsory files which is needed to run the simulation. And after the case is stored, we have 2 options how to run the simulation. So first we can generate a computational mesh by building components separately, or we can click on the mesh all button to mesh all geometry, and afterwards we can run the calculation, or we can run all these steps by one click, which is here run all. So this is a part of an automatic run. So for example, I can first click on mesh all. So now the meshing is in progress, and you are always informed of the process, of the current state of the process. So now the component 1 is meshing. So if I a little bit jump in time, which is here, so this is the step when the meshing process is done. So afterwards you can visualize the mesh. For example, I can visualize the volute with the component 3, which is the connection between impeller and the volute. So if I check the show button and click on apply, so now I can see the mesh. Okay, so if I am satisfied with the mesh, I can now easily click on the run calculation, and the calculation will run. So always during the computation you are informed which point is currently computed, the estimated time of the computation, and so on. Anytime during the computation you can click on update report and see the current state of the simulation. But anyway, at the end of the computation, which I have here, you can see that all progress bars show us that the process is done, and the report is updated automatically at the end, and we can check it here directly inside the ParaView. So this is the automatically report which shows you all important information about the simulation. So because we simulated 3 speed lines, so first there is 3 figures which shows you the overall properties of the compressor and of the results. So first one shows you efficiency for each speed line, total pressure difference for each speed line, and of course for each point of the simulation. And the last one but not least is the total pressure ratio. Okay, and then afterward there is the detailed information for each speed line. For example, flow rate within the simulation, so for each iteration. So you can see the convergence process for each point, residuals for each variable. Sorry, you can read, for example, detailed information about the mesh. So all parameters of the mesh, like skewness or non-orthogonality and so on, Y+ parameter, and detailed information both in the form of the table for each point, and also in the form of figures and graphs. Sorry. So efficiencies, torques, total pressure, and so on. So all important information are listed here in the report. But anyway, you can also do visualization, post-processing, or you can visualize the results directly inside the ParaView. So for example, I have prepared some visualization using the filters which are standardly available in ParaView. So you can visualize any part of the geometry. You can visualize any field, any computed field, for example, temperature. You can make the slices in any part of the geometry. You can visualize, for example, the glyphs, the vectors of the velocities at these slices. You can generate the volume streamlines at the blade, for example, or you can visualize the pressure contours on the blade. So this was example of standard filters in ParaView, and we have also developed the turbomachinery filters. So basically this is just the walls of the impeller, and if you apply this turbo unwrap filter, you can unwrap it and have so-called blade-to-blade view of the impeller. For example, with static pressure distribution, you can create a slice, the radial slice, in any and at any radial coordinates of the blade, you can visualize the streamlines with total pressure distribution. And moreover, you can also create the meridional average on the blade with, for example, total pressure distribution. So all this can be done directly in ParaView. So I see that my time is almost up. So have you seen, the TCFD is a great, easy to use and powerful tool for detailed evaluation and validation of your geometries. In CFturbo, you can design your machine, and then by few clicks, even without any deep knowledge of CFD, you are able to validate your geometry. So the process from the get data to the data to the data which is imported in CFD is really fast. And on the other hand, TCFD can be also scripted and therefore easily incorporated into your current CFD workflow. So it can be really modified to your needs. So my time is up. Thank you for your attention, and I have to hand the presentation back to Luboš. So Luboš, can I hand it back?
Yes, absolutely. Yeah.
Perfect. So now I hand it to you. Okay.
Okay, thanks. So yeah. Thank you, Radek, for your live example. And now it's time for the questions and comments. So we will open the questions and comments, and we will answer them. So give me a second. There are questions right here. We have several questions already. So anyway, I would like to remind all the attendees that now it's really the time to put your questions. So feel free to put your questions, and we are going to answer them right now. So yeah. So there are. Okay, I will start. So, what is the rep and lean angles from Mr. Taha Poonwala? Oliver, would you answer this answer to the all audience?
Yes, I will. The rep angle of the impeller is just the tangential difference between leading and trailing edge at a special span. So if you can make me a presenter again, I can show it also in CFturbo. Okay. I have opened the meanline design step again. Here's the 3D preview, and one can see it especially in the frontal view. That's the frontal view, and I probably only have one blade. And if you look at the blue mean line of the main blade, there is a difference in tangential direction, which is that one, between leading and trailing edge, and I can directly change it and make it smaller to the Hall, for instance, and you will see immediately how it looks like. Well, maybe the other direction would be better, 140, and that's just this difference is the rep angle. And the other one is the lean angle, and here I use again the rake angle is the lean angle at the outer diameter, and you see here it's very much kind of banded, and I can lower this lean angle by having the rep angle again smaller, and you see here now this is much less banded, and the lean angle or the rake angle, because that's the last lean angle, is smaller. And if I have 60-degree rep angle, it's almost it goes in the other direction. So maybe 70 is good to have almost zero lean angle or rake angle here. Thanks.
Okay. So the questions here. Okay. Yes. So the next question is the same question, Mr. Taha. Where can we? Where can we specify the location of the splitter blades?
Okay, it's again to be done here in the mean line design step. So, for instance, the leading edge position can be defined by a relative value, which gives the position between two adjacent main blades. That's one thing. And the other thing is, of course, the meridional location of the splitter is just to be defined in the meridional design step just by grabbing control points of the splitter blade.
Okay. Okay. Very well. So and then we have a couple of questions from Markus Kollmann. Hello, Markus, and good morning to Gunskirchen. So I will read the question number one: how to define a spreading over different calc servers in the GUI directly in the TCFD file? It's possible with the host command. And how to do that with graphical interface. Radek, would you answer it, or do we know it?
Yes, sure. Yeah, I know it, and I can answer it. What the problem is now that I'm using the Windows version, and inside the Windows version, there is no possible way how to define it. Thank you. Yeah, so inside it is inside the simulation part. Yeah, here, if you are in the Linux version, so here there is an additional window in which you can set the names or IP address of your machine, of your servers, and afterwards it is splitted and distributed to all these nodes, computed nodes, and can be run in parallel on different CPUs or different nodes. So this is not available in the Windows version, but it is available inside the Linux version.
Okay, so So thanks for this. The next question from Marcus is it possible to define multiple inlets or outlets in the geometry?
Yes, it is possible. I don't know if you now if Marcus means the multiple inlets between components. For example, if we add the leakage part, so then leakage and from the impeller inflows to one component, which is connected to these two. So this is possible, and in general, yeah, I think it is possible. But then within the graphical user interface, these multiple inlets or outlets has the same inlet boundary or outlet boundary condition, which is set it.
I think so. I think the same. Okay, so in general it is possible, but the boundary condition is the same. Has to be the same with current version. And the last one from Marcus is it possible to show the convergence of each point separately, not the whole speed line?
Okay, within the graphical user interface, so within the report, this is not possible at the moment. So it shows overall convergence for speed line. But if you go into the case, into the computed case, into the logs directory, I don't know if my screen is shared. Do you see my screen, Luboš?
Yes, we do.
Okay,
Yeah, go ahead.
So inside the logs, for example, if I am interested in, for example, convergence of X component of velocity, so I can go inside, and here is the initial residual for each iteration. So for example, if I extract just the iteration from 0 to 4000. So it shows me the convergence process for first point in the first speed line. Yeah, so it can be post-process, but at the moment it is not available in the automatic report generation.
Okay, thank you for this. And another question on Radek is, can the meshing software generate both structured and unstructured meshes from Mr. Thomas Andrew?
Okay, well, because the software is using the SnappyX mesh, or it uses SnappyX mesh, and SnappyX mesh is the meshing tool which creates hexadominant but unstructured mesh. So the structured mesh is not possible to generate it directly within the TCFD. So if you would like to use the structured mesh, you should, at this moment, you should use the external meshing tool, meshing software, and then it can be converged or and input into the TCFD.
Okay, thanks for this. The next question, can the computation be set up to run in parallel on multiple cores? The same question, right?
So, yeah, the same question as I answered already. So it is available in the Linux version without no limitation, and it is not possible inside the Windows version.
Okay, and perhaps the question is asking if you can run multiple cores. So the question is yes, you can run on any number of cores. Okay, of course, yeah. Yes. It's standard CFD tool, so you can run, you can employ any number of cores you want. The next question, is there any special module provided in this software to work on mixture or two or several gases? Maybe I can answer this. The current TCFD version uses an ideal gas approach, so no mixtures or real gases yet. Yeah,
but if I can add to this, because OpenFOAM provides some feature for mixed gases, but it is not implicitly available in the graphical user interface. But if it is possible in OpenFOAM, it can be scripted. Yes.
Okay.
With more or less work, it would be possible. But
okay.
At the moment, I can't surely say that it is possible or not.
Okay. Okay, so it would be a matter of some analysis. And perhaps the last question is, how can I use this software for energetics evaluation of the radial compressor? If yes, how? From Mr. Adonak Londo. I'm not sure I understand this question. So the radial compressor can be evaluated in turbomachinery CFD by the simulation. So I think that's what we've shown already, basically. So yeah, the very last question is, does the software have adjoint solver? From Thomas, no, it has not the adjoint solver. If you mean the optimization tool or this, it's in the process. We believe before the end of the year we will introduce the optimization tool, which works well together with turbomachinery CFD, but it's not there yet. Yeah, I will quit here with answering of course there are some other details, but I think this is it. I think we should conclude. So I will take the presentation back to me, and I'm gonna finish. So this was the Q&A session. We have answered the questions. So yeah, it's time to finish, so feel free to contact us. I'm sure you know very well how to do that. The questions about the CFturbo are to be sent to CFturbo company. The questions about turbomachinery CFD software are about to be sent to CFD support. We will gladly answer all your questions. We will answer everything. We will gladly support you in your turbomachinery projects. It's our job and also a pleasure for us. So I think this is it. So anything more to say? Oliver, would you?
I just want to say thank you for your attention, and I hope that we can get in touch sooner or later. Thank you. Bye-bye.
Okay, and Radek, would you add anything?
Yeah, I will follow the Oliver's words. So thank you for your attention, and please feel free to contact us. We are here for you, and we can help with your needs and with your problems. Thank you.
Okay, very well. All right. So the same for me. So we would like to thank you for your attention. We are looking forward to collaborating with you. So stay tuned and bye bye for now. Bye bye.